Oviedo, and then he has a PhD degree from the Open University in Madrid. His supervisor was Javier de la Rubia, some of us. Then he stayed in the Instituto for Non-linear Science in La Jolla in San Diego, collaborating with Hagen Lindenberg, and then Institute for Mathematics in Oxford, and then he spent 2 years at the IFISC, this Institute for Mathematical Sciences at Madrid, but he was from the CSIC side. He was from the CSIC then. And nowadays he's at the Department of Economic Analysis at the Autonomous of Madrid, and still at the IFISC. His work mainly on problems of statistical physics, also with biological applications that we see today. I know his work on the viruses, relative motion, and then he also has some more mathematical oriented side, pure study of the equation with applications. Recently, he was awarded the Young Researchers Prize of the Royal Spanish Physical Society for theoretical physics, the Young Prize for theoretical physics. And today he wants to tell us about this amazing growth of
First of all, I would like to thank Raul for the invitation and for the kind introduction. It's as always a great pleasure for me being here. And today I will talk about a topic which is rather technical. I will try to focus on physical details rather than on technicalities, and this will be possible mainly at the beginning, but at some point we will find some technical difficulties. Yes, to be completely honest, we have this word morphogenesis in the title. Well, I refer to mathematical morphogenesis. Okay, this is a pure statistical mechanical problem. It is not really related to biology. It is inspired in biology. So, I will start anyway telling a few things about the history of problems inspired in biology. Very long ago, people found these striking relations between Fibonacci numbers and the related golden ratio, which are pure mathematical things, and pattern formation in nature. For instance, one can build logarithmic spirals as this golden spiral built with proportions of the golden ratio, and logarithmic spirals are found in some seashells, and also Fibonacci numbers. They have a very interesting relation with phyllotaxis. For instance, patterns in sunflowers have spirals spinning in both directions, both clockwise and counterclockwise. These spirals actually they are parabolic spirals. The angle of divergence is the golden angle, and they have well, the number in both directions is different, and actually the number is usually they are adjacent Fibonacci numbers. These observations motivated the work of a lot of people. Sorry, like for instance, Darcy Thompson. Okay, he wrote a famous book on growth and form. For some people, this is the first book on mathematical biology in history, and it's a long book. For instance, there's an interesting chapter about shape of animals. He drew for instance, the skulls of different species of crocodiles on lattices, and he showed that simple transformations of the lattice connected different species of crocodiles, and this is also the same for several species of fishes and other natural species. And also Fibonacci numbers were the starting point for the interest of Alan Turing. He's a very famous mathematician, on the morphogenesis, on how the form develops in biology. And he has a very influential paper in which he considers systems of reaction-diffusion equations which possess an instability, diffusion-mediated instability, from which from a uniform substrate, the uniform substrate, okay, so the initial condition becomes unstable, and a pattern like this appears. And for many years, people used this instability and related mechanisms to try to explain the patterns in animal codes. Now it's kind of clear that it's not, at least a pure Turing instability, the reason of such patterns. But anyway, the work is very influential. Well, anyway, I am not concentrating here on this part of the article, on pattern formation or Turing instability. But if you read the introduction of this article, you find very interesting thoughts by Turing. He considers the following problem. An embryo, right? An embryo of any animal species is, at the beginning, consists of a lot of cells isotropically and stochastically propagating. So he said, okay, proliferation is isotropic, we have a spherical symmetry. Then, at late stages of development, the embryo, for instance, the embryo of a horse is horse-shaped. So something happens in between which breaks the spherical symmetry. Well, so this was the motivation for him to develop the instability. But if one wants to be completely precise, at the very beginning, when the proliferation of cells is stochastic and isotropic, one doesn't need to have a spherical profile. Okay, in average, there is a spherical symmetry, but every single realization of the process can be symmetry breaking or symmetry preserving. Yes? Oh, because you add a new cell following a certain probabilistic rule.
No, they divide. They divide.
Well, I mean, this is mathematical idealization. Turing did not do. He didn't do a very detailed modeling. Okay, they divide. So initially it's added, and he assumed that it's well, in the reasoning, that this addition is kind of stochastic.
But that was 50 years ago. Now we know that it's not like that.
Yeah, sure, but I mean, well, I did not concentrate on real biological processes. So, anyway, what I say is that if you have a process like this, okay, this can be very idealized, very simple. You don't need to have spherical symmetry. Okay, if you average over many rotations, indeed you have spherical symmetry. If you consider single rotations, not necessarily. Okay, yeah? The process of fluctuations might drive the system out of the spherical symmetry. Mainly if we go to low-dimensional systems. Okay, we know a lot about fluctuations from the study of phase transitions, and we know that in very high dimensions, mean fields usually holds, but in low dimensions, fluctuations can have very important, even dramatic effects. And this observation by Turing is related to the model introduced by Eden also long ago. The idea is the following. We have a lattice, say set n, and I will, of course, for ease of representation, I'm concentrating here of the case C2. We have the origin is an infected site.
So could you try with the blood, right?
The pardon?
Could you try with the blood, right?
Okay, sure. Okay, so the origin is infected and the rest of the sites are free of infection. And sites which are adjacent to an infected site become infected following certain probabilistic rules. So you get more and more infected sites. If you iterate the rule for very long times, you find these concentrically growing interfaces. So this somehow, this is a way of formalizing the problem I mentioned before. This is not.
So what is an interface? What is an interface?
The interface is the curve separating infection from the sites which are free from infection.
Has a width as well.
Yes, it does.
Yes. What is the connection between infection and morphogenesis?
No, I mean this is it's a way of I can express itself. I think I don't know. Maybe it's not very fortunate. Okay, this is a way of explaining how the model works. Okay, you can say that the site is occupied and then new sites are occupied. You can think of cells dividing here, occupying new sites. But anyway, I mean, this is a really probabilistic thing.
The color, which is the meaning of the color, just time or
Yeah, exactly.
different times.
Yes. So he didn't want to analyze the problem by Turing, but a different problem, which is actually, well, the formalization are very related actually. The problem by Eden was the problem of twins. Okay, twins are individuals of the same species which look very much like each other if you consider them as overall individuals. But if you look small scale properties of twins, okay, then differences arise. For instance, fingerprints are usually different. And if you go to some smaller scale, like for instance, patterns of retinal finiation, okay, in the eyes, they are more different. And if you look to the actual cell distribution, then this is completely different. So, how can we formalize this in a pure statistical mechanic or probabilistic way? Like this. If we consider different realizations of the stochastic process, the actual cell distribution is completely different. Okay, but asymptotically, they have the same shape. So, as I said, this is not real morphogenesis. If you want to have real morphogenesis, you have to put here a lot of laws of chemistry, physics, biology. So this is a pure probabilistic or statistical mechanic formalization of the problem of twins. Even if you have different rules, okay, the asymptotic shape can be the same. So, if we speak in mathematical terms, we have different set of rules which form a Bayesian of attraction corresponding a certain statistical attractor. In physical terms, we have universality classes. Well, what are the different asymptotic profiles? In the simplest terms, we have two. One which preserves spherical symmetry and one which breaks the spherical symmetry. We will try to do a finer analysis and actually quantify how much the spherical symmetry is broken. And as I said, this can be thought as a statistical mechanical problem inspired in biology, but not necessarily. Actually, it is related to percolation theory. Percolation theory is a branch of statistical mechanics and probability theory. And actually, the Eden model is nothing but a sort of percolation known as first passage percolation. Okay, I will focus here mostly on the physical motivation for percolation as related to the current problem. So we have some porous medium, for instance a rock, and we inject liquid in some point. Okay, if the permeability of the rock is constant, we have spherically symmetric, concentrically interfaces propagating. But actual probabilities are random and very complicated. So if one does the experiment, one finds that the wet part of the rock forms a complex fractal structure. Between this and these extreme cases, one finds, of course, intermediate cases, and we will focus right on the threshold in which the radial profile loses the stability, right? Not on this case where the fractality is completely developed. To do this, we will adapt a theory which is well known in a different context, but it has the same, the underlying idea is basically the same, and this is that of stochastic growth phenomena. In this case, we have, for instance, some paper which becomes wet by ink. So we can see the profiles of the wetting front that are rough and actually fractal. So in this case, the flat profile, which is the uniform profile, the symmetric profile, is unstable, and a fractal profile is stable. To describe this mathematically, one uses the function height. Okay, at any point in the substrate, one assigns a height, and this height, of course, depends from time to time, changes from time to time. Well, the basic phenomenology is very well known now, and well, the basic magnitude of interest is the function width. The function width is nothing but the standard deviation of interface. Okay, and it is well known that it, for many systems of interest, it adopts this self-similar form, in which L is the linear size of the substrate and T is time. Furthermore, we know the asymptotics of the scaling function f. As shown in this picture, for short times we have width grows like t over beta. Beta is a real number known as critical exponent, and for very long times the width saturates. It doesn't grow in time anymore, but it depends on the linear substrate size, like a power law, with different exponent alpha, which is again a real number. So this means, as I said, that we have this power law growth of the width for short times, and then we can look at very long times the constant width interface, which amplitude depends on the value of alpha. Actually, the physical meaning of alpha is the following. For instance, alpha 1/2, we have this kind of long-range oscillations, which become more and more pronounced as the value of alpha increases. And well, for comparison, this is a path of Brownian motion, which if we consider this stochastic process within this framework, it has alpha equal 1/2. Well, what is the connection with the problem we mentioned at the beginning? Once we are in this regime, in the saturated regime, if alpha is positive, and we consider the asymptotic case of a very large substrate size, then the amplitude of the oscillation, the width, increases, right? So the fractal profile is stable, and the flat profile, the symmetric profile, is unstable. If and also we have a way of quantifying how much the flat symmetry is broken. The larger alpha, then the deviation from the flat shape is larger. If alpha is negative, then one in principle should expect some sort of convergence. When L goes to infinity, some sort of convergence of the width to a flat profile that would become stable. Okay, this is actually tricky because this is pure scaling. If we will always consider white noise-driven models. In this case, there is a prefactor that when alpha is negative becomes infinite. So there is one cannot expect any kind of convergence to a flat state because the width is infinite. Anyway, this is a subtle point, and I hope it will become clearer in the following. But this is the connection between both problems.
Yes, I don't know if it will be important or not in the following. You are going to take, I don't know if this will pop up later, to say that the flat profile is unstable and the fractal one is stable. So you only mean that the flat profile is not maintained in time.
Yes.
But the usual models, if you do the linear stability analysis, the flat profile is either stable or marginally stable. It's never unstable in the usual end.
Yes.
Yes, but you mean that in the presence of some kind of noise,
yes,
the flat profile is not maintained.
Yeah. I'm using the terms.
Not related to linear stability or instability.
No, that's true. I'm using the terms in a loose manner. Yeah, I was not trying to be completely precise. But the idea is that, I just want to express the physical idea. If we have positive alpha, so very large size, actually asymptotically large, we have a profile which is very different from the flat one. Okay, if alpha is negative and we didn't have this problem, then we should expect some kind of convergence to the flat profile.
Did you say that you could never have a surface which is flat?
If you have
a stochastic growth model.
If you have white noise, if you have some smoother noise, it is possible that you can. But with white noise, at least the models I have studied, with no one model you have a flat profile in the sense that the width goes to 0. Okay. In scaling, it goes to 0. But if you consider the perfactor is divergent. Yeah. It's different if you run a discrete model, the simulation of a discrete model, because this somehow regularizes the microscopic properties of white noise. But if you consider actual white noise, you can, well, I can show you the calculation and you find divergence here. Okay. So. And now we move to the quantity of interest. For us, the quantity of interest is the height correlation. So this quantity measures how the height in one point and at one instant of time affects the height at a different point at the same instant of time. Okay, in these models, this correlation adopts this self-similar form, which is very much similar to the scaling form of the width. Okay, the exponents are actually the same, and the asymptotics are actually the same. And we have, well, in a large and important number of cases, that this relation holds. Okay, between the exponents defined before, beta is equal to the ratio alpha divided by Z. Now, theoretical models that have been employed in this context and which define different sets of exponents, which are known as universality classes. Simplest one is the Edwards-Wilkinson equation, which is nothing but a diffusion equation driven by white noise, and exponents can be exactly calculated in any dimension. I just wrote them in d equal 1, but we have the exact result because the equation is exactly solvable. Mullis-Carrin equation, which is a higher order counterpart of the diffusion equation. We have again exactly solvable model which exponents exact in any dimension. KPC equation, which is a nonlinear counterpart of the first equation. We have exact exponents in one dimension and lots of open problems in higher dimensions. And Villen-Leydesarma equation, which is kind of nonlinear counterpart of the second equation, and in this case we have approximate exponents in any dimension, but with a good accuracy. Our goal will be adapting these equations to a spherical format and then getting conclusions on the convergence to a symmetric profile or divergence from this symmetric profile. More quantities that are of interest. One is the autocorrelation function, which in this case we consider height correlations at the same point but different instant of time. This 0 here, okay, means that we are suppressing the 0th mode, the uniform translation mode. And well, we have a normalization which depends on the standard deviation at both space-time points. In the limit t prime much greater than t, this formulation adopts this power law form, okay, with an exponent alpha, which for linear models can be computed exactly, but it also holds for nonlinear models. This is an exact result, which depends first on beta, which measures, as we saw, it measures the amplitude of fluctuations, plus d, which is the spatial dimension divided by z. This measures, just let me go back a second. You see that the scaling form will saturate when t is approximately equal to L to Z. Okay, so we can say that correlations propagate like a power law t to 1 over Z. Okay, so 1 over Z is in power law terms the speed at which correlations run away, and v is the ways of the different directions in which correlations can scale. So this ratio measures how fast correlations can scale from one given point. And of course, the larger the lambda is, okay, the faster the memory is lost. And one last exponent, which is the persisting exponent, this is more technical issue. So we have, for instance, one profile at T1, a different profile at T2. In this case, the persistence probability is the probability that the same point, which has this location at T1, in the full interval T1, T2 is always above this position. Of course, in this case, we have also to subtract the zeroth mode, which is the uniform special mode. Otherwise, the problem becomes actually kind of trivial. And these measures, okay, we also can define it, not just the probability of being from above, but for being for being below. In the cases we will study, okay, interfaces are symmetric, so the probability is the same, but this is not general. This measures the persistence of the process. This is the tendency to continue in a given trend. If we perform the calculation for any of the questions we have seen, one finds this just for linear equations, or just for linear equations, and particularly in this quantity. This should be very small, and sorry, this should be a set, not a zeta. If theta is equal to 1/2, this is a neutrally persistent process. Okay, so the probability of being above and below the initial time, the profile at the initial time is the same. If zeta is greater than 1/2, like in this case, then the process is anti-persistent. Okay. The probability falls in a sharper way. This is always larger because this is always a positive quantity. And again, we have this factor that measures how fast correlation scales from a given point. Physically, this means that we have a diffusion acting on the interface, which is pushing the interface back. Our diffusion tries to make the interface go back to the original, well, actually to the flat case, and we have this anti-persistent behavior. If we had something smaller than 1/2, we would have persistent behavior. Well, now we move to the topic of interest, and we want to answer several questions which are have technical origin, but we in turn gives the desired answer of the problem. Okay, we will try to see if the exponents are the same, if the scaling form is the same, what happens with correlations in space and time, and what happens with persistence. We will start first.
But the same than what? They are the same than what? The exponents are the same than?
Okay, in the classical form, you know, in which we describe something from a Cartesian reference frame, we have this Planar profile, and now we will move to the radial profile. Okay, and try to see if the same equations have the same properties or different properties. But we will do an intermediate state, because moving directly to radial things is quite complicated. Okay, so we will do something in between, which is much simpler, and which is studying the dynamics of these equations on domains which grow uniformly in time. So we start with this diffusion equation with the white noise source. We can write this equation as a conservation law in interval form. Okay. Now, if we want to express the conservation law in a local form, we have to interchange integration and derivation. Because the domain is uniformly growing in time, we pay a price of interchanging the derivative and the integral. And the price is this quantity, which is given by Reynolds transport theorem. So, once we have done this, we have these terms which are equal, and they hold in any domain, in any growing domain. So the equality must hold point-wise too. Okay, so we can actually have our PV. Coming from here, we get this PV, which is to be solved on a growing domain, and we have this mu term.
Sorry, I don't understand what is the quotic F. Then what is V?
Okay, yes, I probably was a little bit fast here. This F is it's a shorthand notation for constant F plus white noise. Actually, the derivation is more general, so F can be anything which depends just on Y, which is the position of the substrate, and T, time. And the derivation, as I said, is more general, and we don't need to have actually the Laplacian diffusion here. We can have any divergence of a current. If we assume Fick's law, then we have this, but it holds for much more general formulation. So I just wanted to express this like general conservation law in integral form. So we very much don't care about the generalizations in this case. But if we substitute now J, the gradient of H here, and then this quotic F by white noise plus constant drift, then we get the right hand side of the equation.
V?
V, yes, V is the velocity which is generated as the domain grows. Okay, I will now go into the details of V. First, let me say that we can find two terms out of the new term which appeared. First is an afflection term, and second one is a dilution term. So as the domain grows, there is an affection. Matter is affected towards the direction of growth, and the mass is distributed on a larger volume. Okay, so the mass becomes diluted, and this is given by this term. Now, which is the form? What is the concrete form of V, the velocity? We have y, the position of some time t, is equal to the growth factor g of t, which we only consider uniform growth, So this is a function of t, not of space, and y naught, which is the initial position. The velocity is the derivative of y with respect to time. So we have v is equal to g prime y naught, and this is g prime divided by g y. This is our velocity.
I'm getting lost. Y is the direction on the surface, right?
Yes. This is the position in this direction. Is y. And in 1D,
So what's y of t?
because it depends on time, because things are
How is
really
it growing? From outwards or the surface? How's it growing?
yeah. Well, it's growing transversally to the growth direction. I don't know if this is clear. We have this is y and this is h. And
Why is it coming to time?
yeah, because if things are growing uniformly, you know, at time 0 you are here, and then this same point, this same position after some time is here. It's a dilatation transformation in the sense that everything we are not simply adding some empty space here. We are kind of stretching the substrate.
What is the boundary condition?
Of any kind of boundary condition. What I all the time, well, at the end, I will be using periodic boundary conditions when I move to the radial situation. Okay. For now, I'm using no flux boundary conditions.
I thought the aim of your comparison was the 1D case, where you have an infinite thing which is growing,
Yes.
versus what happens if the thing grows in a radial disk.
Yeah, exactly.
And
But
now you're saying something else.
yeah, no. I mean, this is an intermediate state. Okay, probably I have to be clear. If you consider some radial growth, there are two basic differences from the current growth. One is, well, actually there are three. One is curvature. A different one is topology, which in 1D is the same. Okay, there is nothing about. I mean, this is the topology is the same in a flat torus or in a on a cube with boundary conditions. The topology is the same as that of a torus. Okay, the difference is curvature. So in 1D we don't care. And the other thing, the last thing, is that the length of the domain is growing in time. So this is an abstraction. We will forget about curvature and consider just the uniform growth. This is why. This is because curvature induces nonlinearities, which of course makes things much harder. So the aim is building a linear theory to get inside and then try to build some approximate theory for the nonlinear situation, which is much more difficult. So this is the beginning of the formulation of the problem on a growing domain. Now we will focus on 1D for the derivation, and if we substitute V as I wrote it here, we find this new term, and the rest of terms are familiar. So we still have to solve this PDE on a domain which is growing in time, which is of course difficult. So now we will do a change of variables. We consider a different coordinate x, which is L0, the original size of our interval, divided by L of t, which is the instant size. And here we have the coordinate y, the original coordinate. if we do this change of variables on our equation, first we see that, well, now we have to solve an equation on a fixed domain, which is of course nicer. Second, the abstraction term disappears. Okay, but well, both things are very nice, but we have to pay a price, which is we get this explicit time dependence of the coefficients of the equation. There is a last assumption for simplicity in this case, which is that the growth factor g of t will be t over t naught to the power of gamma. Gamma is any real number, will be a real number strictly greater than 0. Okay? If we make it 0, we have the classical case. Why we are employing a power law? As I said, correlations travel like t over z, a power law. So we will compare both ways of the different ways in which information can travel across the system. One is the correlation length, and the other thing is domain growth. So, because one is power law, we assume the other one is a power law. Finally, all we have done here in 1D and with the Laplacian can be greatly generalized to the d-dimensional case, any special dimension, and also we have substituted the Laplacian by a fractional Laplacian.
Sorry, I don't see the difference. What is L of t and G of t? What's the difference?
This G of t, okay, is the growth factor.
And L of t?
Is the instant size, the actual size of the domain. So we have the following relation: L of t is G of t L naught. Okay. Finally, the equation. We have this fractional power of the Laplacian. Why are we substituting the Laplacian by a fractional power of the Laplacian? Because if we consider the case in which the domain is static, the dynamic exponent z is identically equal to zeta. To zeta here, sorry. So we can systematically study the dynamics as the dynamic exponent z is changing and as gamma, the growth exponent, is changing. This is to be interpreted in the Fourier transform sense. This is a linear operator, so if we well, a minus sign is lying here. If we transform this Fourier, then instead of nabla, we have k. This is the correct interpretation of the operator. Furthermore, well, this is not just a mathematical trick, just to get the desired dynamic exponent, but this appears also in well, it has a very clear physical meaning, at least for several values of zeta. It is the description of an anomalous random walk. For instance, Levy flights. You have a random walker in which I will not introduce precisely Levy flights. You have long flights instead of the small steps of a classical random walker. The description, the hydrodynamical description of a density behaving this way comes by means of this kind of operators. Okay. Well, this is not the only way of making a substrate grow. There is another way, which is nicely described in this paper. With this, in fact, more general. They study reparametrization invariance of stochastic growth equations. This means that they write the equations in a coordinate-independent fashion. They write equations which hold for any kind of manifold. So we don't need actually to have some average flat geometry for the growth process, but we can have spherical, hyperbolic, anything. And without entering in the details of this, which at some point become quite technical too, one has the equations written in this very general form. If we want to have the 2D radial growth, we just need to assume a polar parameterization. And this, this has been employed, this technique has been employed in several papers to study radial growth. Okay,
which one of those or Vasily ones?
all of them. In all of them, this kind of extension of the theory from planar substrates to radial substrates have been employed, this reparameterization invariance. What is the difference? Now we can use reparameterization invariance not to study a radial domain, but a growing domain. So the question is, what is the difference between both descriptions? The difference, and this is important, and going back now, we get exactly the same equation, okay, but this term is lacking. There is no dilution term. I will tell physically what it means and what are the consequences of this. So, in principle, we have two different ways of extending the planar theory to the radial symmetry or the growing domain symmetry. But this is not surprising in the sense that we are generalizing a theory, and generalizations are not necessarily unique, of course. Differences. The simplest and more intuitive one. Let's consider now pure diffusion without any noise on a growing domain. This is what we have if we introduce dilution. In this case, we can study conservation of mass, which is probably the basic quantity in a diffusion process. In this case, mass is conserved. Okay? The calculation is explicit and mass is conserved. However, if we neglect this term, we find that mass is not conserved. Actually, mass grows at the same rate as the domain grows. Okay, so physical difference between both. If we have dilution, mass is always the same, global mass. If we don't have dilution, we have dilatation of space and mass simultaneously. This is this is very intuitive, but it's not actually very important for the process, for the stochastic process. But there are very important consequences of this. Why? Because if we have some constant source plus a white noise here, this addition of mass is subdominant. So asymptotically, we can neglect it. We can neglect it. But more important differences. The equations are linear. The coefficients depend on time, but not on space. So we can, in some way, Fourier transform them. Actually, we use a Fourier series. This means that I'm solving the problem on a bounded domain. Actually, on a hypercube. One thing that, I will not enter into details, but solving these equations with Fourier series is somehow technical, because this is a fractional operator and poses certain problems that our Laplacian does not pose. I'm not entering into details of how to solve this, which is a pure technical question. I just wanted to mention it. Anyway, we have a solution in terms of Fourier series, and we have one part which depends on the initial condition and another part which depends on the non-autonomous part. And this is the case for dilution, and this is the case for the absence of dilution. Very important. Very important. We are assuming that gamma is greater than 1 over zeta here. If we use the reverse inequality, we have that the initial condition for every mode decreases exponentially fast in time. This is the initial condition is diffusing. This is an effect of pure diffusion. in the case in which gamma is large enough, well, here we don't have an exponential decay of the initial condition, but a power law decay. Okay, and the exponent is minus the gamma. So the initial condition is no longer diffusing, but is becoming diluted. If we forget about dilution, we have that the initial condition is damped, but anyway, a fraction of it persists for all times. So very strong memory effects. How does this affect scaling? Well, this is a natural length scale. Well, from now on, I will focus always in the case of fast growth, which, well, this is where the real differences arise. If we revert inequality, things are much more similar to the classical case. There is a natural length scale which appears in this case, which goes like t over 1 over zeta minus gamma. This is the ratio of how correlations propagate and how the domain grows, velocity of both. If we focus on the case, on length scales which are much greater than this length scale, what we find is a Dirac delta correlation, which t-dependent per factor. This comes from the zero mode, uniform translation. And if we look at very small length scales when compared with this characteristic length scale, we find actually the family IFISC scale, the classical situation. One thing that can be argued is that, well, we are missing intermediate asymptotics here, but anyway, if we take the limit of large distance in this self-similar form, we get this thing. So one can say nothing is new here, right? We are recovering perfectly the classical case. It's just two limits of the same thing. Well, this is not clear at all. Actually, because much more general forms will converge to this thing. And actually, this has some indication that the form should be different. So, well, if time allows, I will explain everything in detail. So, suppressing the zero mode, we have this T Dirac delta, which means there is no correlation. This is in the case we introduce dilution. If we suppress dilution, we have something different. We have actually dependence on the dimension of the system. Okay, if gamma is smaller than 1 over d, we still recover the same form. But if not, we have a larger factor, which comes actually from the increase of mass in the system. This is a measure of this new mass that is entering the system. And so, how much time do I have? 5 minutes. So I will probably suppress part of the talk. Just very briefly, if I calculate again exactly lambda, then I find in the case of dilution that if gamma is subcritical, exactly the same value from the classical case. If gamma is supercritical, 1 over zeta is substituted by gamma. So correlations, okay, this reveals that correlations are no longer propagated by the effect of diffusion, but by the effect of dilution. If we forget about dilution, okay, in the other case, we have this form, which is, well, we have the same form as in the classical case, but with an effective set, which only if gamma equals 0 is the same. If no, if grows monotonically till gamma is equal to 1 over zeta, in which we find a divergence. So lambda equal beta, and we effectively have no connection between the different points in the interface. Again, one sees here very strong memory effects. Here, large gamma yields a very fast loss of memory. Large lambda. Here we have a smaller lambda. So memory is retained. For persistence, exactly the same. we consider dilution. Again, this is for linear models, and this part is considered as a perturbation in both cases. This is the case with dilution. We have this d gamma here, which make this value much larger than 1/2. So the interface is anti-persistent and more anti-persistent than in the classical case. In this other case, we have that theta is smaller than 1/2. So the interface changed from being anti-persistent to being persistent. So the full behavior of the interface is different. And well, I will skip this because there's no time. Okay, now I review the scaling and tell about convergence properties. Classical case, we have this family big scaling, self-similar scaling, which is invariant to this transformation. We dilatate space, time, and field, and the form is invariant. If we, of course, choose the right scaling exponents, and this scaling law is fulfilled. If we study this equation, this is linear diffusion equation with any fractional operator, we can find exactly the exponents, which are like this. This means that this the order of the fractional operator fixes the dynamical exponent, and then both alpha and beta just are a function of the dimension of the system and zeta. What happens if we move to a radial interface? I have skipped a lot of details because, well, if I have to do the calculations, then we would be several days discussing this problem. What we have done is deriving radial equations using reparametrization invariance. Then, as I said, the equation is nonlinear and very difficult to solve. So we find a deterministic solution for very small nodes, which is spherically symmetric. And we consider fluctuations as a small perturbation. The equation for the perturbation is rho. And we have something which is very similar to the equations we have been studying without dilution, with the fractional Laplacian, and well, the dependence is on angle theta, but this is more or less the same as our x, right? And if we move to arc length coordinates, it's the same of our y. Now we have a spherical noise, or in general dimension, this is hyperspherical noise. And it should be normalized. Well, there are several ways of seeing this, but reparametrization invariance immediately gives this minus square root of, or 1 over square root of the Jacobian, which comes, for instance, explaining it in loose terms, from the change of variables from the Cartesian reference frame to the polar reference frame. Okay, this is, well, just the Jacobian determinant for any hyperspherical surface in dimension d. And in this case, we consider with this angle correlation function. We can calculate the correlations exactly for arc lengths of size 1, which corresponds to large distances with respect to the growing domain situation. In this case, we have these exact results, which fully agree with the case we have examined before, but of course with the presence of the determinant of the Jacobian. If we introduce dilution, we will get something which is exactly similar to what we found. Okay, that we have just the first part, the first part uniformly gamma, no division of depending of how gamma compares with the dimension. So in here we have expressed things in arc length differences, not in angle differences. But as I said, morally this is identically the same as considering the x coordinate and the y coordinates. So now we have the asymptotic forms. This is in terms of angles, differences of order 1 in terms of arc length, differences of a Mach length which is comparable with the full length of the system. These are the asymptotic forms. If one looks for scale invariance using the same transformation as in this case, right? As in the classical case, one finds a scale invariance for these exponents. Actually, Z is equal to 1 over gamma, and alpha is exactly the same as in the classical case. Exactly the same but zeta is substituted by 1 over gamma. Again, we have that correlations are not propagated by diffusion, but by domain growth. And we have some beta r here, which is defined. This is not calculated. This is defined as the ratio alpha divided by z. But furthermore, this exponent has a very precise physical meaning. It describes how the center of mass fluctuates. Yet the position, sorry. We have radial interface growing, and if we calculate the position of the center of mass at every time, actually fluctuates. Okay, and the position goes like t to 1 over beta r. So if beta r is positive, what we have is that the amplitude of the oscillation of the walk of the center of mass, the amplitude grows in time. If it is negative, it is getting stuck with time. This is actually a measure of the convergence to the radial profile. If we have a radial profile, perfect radial profile, then the center of mass does not move. Okay? If we are deviating from the spherical symmetry, then we are making the center of mass to perform some kind of random walk. But furthermore, convergence to the spherically symmetrical profile can be calculated directly from alpha. If alpha is positive, then there is a deviation of the average form from the spherical one, and if alpha is negative, as the radial form grows, then there is a convergence to the radial profile. But the subtle point here is the convergence is weak, which is in the title, and so I will just telling you what is weak convergence. So what kind of convergence do we find here? Weak convergence is a term that is used mainly in mathematical analysis, but it has a very clear physical interpretation, and actually in quantum mechanical texts, the same convergence appears and is called convergence in the operator sense. Is the following: if we have for instance, sine of x over L, and we take L, sorry, not to infinity but to 0. If we take L to 0, then we find we find wide oscillations in the region. The limit, actually, I'm sure that everybody knows that the limit doesn't exist. at least in the strong sense. But there is a weak sense in which the limit exists, in which we average over oscillations. And well, precisely, if you have any function f of x, which is, well, basically absolutely integrable, we can indeed calculate this limit when L goes to infinity and it goes to 0. So any kind of average yields that this goes to 0. Okay, so in other terms, there is a weak convergence of this function to 0. In our case, we have delta functions which measure the amplitude of the stochastic oscillations. So these expressions only make sense if we average this against any function. So the limit is necessarily weak. This is not the only way to see this, but well, I hope this is a clear way of doing so. Last point. What is the difference between dilution and not dilution? Okay, if we consider dilution, alpha and beta can become negative. So there is an actual convergence to this radial symmetric profile of any single realization of the process. If we have no dilution, then these exponents can only be positive or 0. They saturate at 0. So there is never a convergence. There is always a marginal contribution to the deviation from the spherical symmetric profile and to the movement of the random walk. The random walk of the center of mass. It never stops. The amplitude saturates, but it never stops. In dilution, the center of mass can stop if dilution is large enough. So, KP set full of open problems. We don't touch it. And conclusions, we have the scaling form is different. Basically, the difference is the Jacobian, which appears here. When we have the radial form, and other, it's not the only one. This is the more evident one. There are other subtle differences, and we have that basically alpha and beta are the same. Well, they have the same dependence on the velocity of propagation of correlation and on the spatial dimension of the system. But what is different is the mechanism that propagates correlations. In the classical case, is the dilution, is the diffusion. If the system grows very fast, we have the dilution mechanism, which is the one which propagates the correlations. I thank you all for your attention.
Any questions?
Yes, this sounds to me something related to what some people does in cosmology. When they talk about inflation, they have the initial fluctuation, and then the thing is growing, and the fluctuations are ironic in time depending on the kind of growth. You have flat asymptotics or not. Will think any of what that have you done related to that?
Well, actually, I just by luck I saw one paper on cosmology, and I saw that they were using uniformly growing domains with this. I forgot the name of the metric, and well, I'm not sure if what is the relation, because they have wave equations, and also they don't have usually noise. What I see is that
they have noise.
Oh, they do. Well, yes, I don't know. I saw one article, and no noise in this article, but of course there should be many articles about this. So maybe there is some relation between this. What I know is that in the article I read, they introduced uniform growth in a very precise manner, and as I showed here, you can introduce the domain growth in many different ways, the growth of the metric in many different ways, and differences can be indeed dramatic, changing, well, for instance, the persistence properties completely. So I don't know if someone looked at this or not, but it's just one thought, because I don't know much about cosmology and mathematics.
Questions? We thank Gracias.